All right, so TCP and Anycast. My name is Matt Levine. I'm a Cache Networks / CacheFly. I'll also be playing the role today of Todd Underwood, since he neglected to show up. But he was actually the driving force behind this presentation. He's been trying to get Bear and I to do something for a year or so, and finally corralled us, but neglected to show himself.
Yeah, so I'm Barrett Lyon. I was formerly with Polec Technologies, and now I'm with a startup called Big Gravity. And I guess we're going to discuss our experiences with TCP and Anycast.
Yeah. So first things first, I know nobody wants to be interactive, but how many people sell IP transit on their network? A bunch. Not that many. Okay, how many of those people are Anycast enabled right now? No hand should have gone down. Anycast from a network perspective is nothing special as far as your routers are concerned. It's just a route with multiple next hops. All the magic that happens with that is on the servers themselves or wherever you're delivering those packets to. But as far as network operators are concerned, Anycast is nothing. It is just a prefix with next hops. That is it. So the perceived problem that seems to be out there is that TCP and Anycast do not play nicely together, especially for long-lived sessions. Porn downloads, anything where you expect that your session is going to last more than 10 minutes, 20 minutes, an hour, 2 hours, some large number. Other presentations have said there appears to be TCP Anycast out there in the world, and we're not really sure why it works or if it works. That's us. So CacheFly, we deployed 2002. We rolled out our first Anycast. Initially, it was just domestic, 3 POPs, 1 on each coast in Chicago. We've since added Japan and Amsterdam. When possible, we keep the same carriers in each location to make sure that we get the bits as close to the eyeball networks as possible. And again, peering, you want to be intelligent about your peering if you're doing anything where you want traffic to be distributed, because oftentimes people's peering maps don't necessarily overlay with where the eyeballs are. In a lot of cases, it might not make sense to peer with people if they actually have more diverse transit connections that will actually deliver the packets closer to where you want. And when you're dealing with your upstreams, it's very helpful if they know what you're doing, and also if they can provide either A, communities in general that help you with your traffic engineering, or B, if they can implement something specific for you or what you need, which allows you to keep the traffic where you want it.
So Anycast is also very easy to proxy. Anything like HTTP proxy server is about the same thing. So a lot of my experience has been moving a lot of people's HTTP traffic through proxy servers, and it works great. Customers are isolated on virtual addresses that live on a load balancer, and that virtual address simply lives in every data center that you're operating on. So when you're looking at the network, it's one block, thousands of customers, and it just makes sense. Now, why would you want to use a proxy server? Would be up to you, but just to relate that to HTTP, it works perfectly. Let's see. So there's a little issue with TCP state, and the reason why you may want to use a proxy server is you can accomplish state synchronization within IP stacks of multiple different types of operating systems. Some of that's done custom, and Matt will talk about what they've done with their load balancing mechanisms. So we'll talk to that a little bit more. Node geography. So when you have good geographical separation, meaning north, south, east, west, or US versus the UK, massive failures tend to not really disrupt anything, because say your traffic disrupts somewhere in Nevada or somewhere in the west coast of the US, chances are if you have one POP in California, the bits are still going to go to that one POP. They just might be going there via a different route. If you have multiple POPs in California, then the chances of you having your stuff kind of get out of state is much higher. So coastal countries work really well. Nodes that are nearby, so the more nodes you have, so if you have 15,000 web servers in the US, chances are that's going to become a problem for you. I added this little slide today because of David Huberman. We had a little discussion about how Anycast might be wasteful to IP space specifically because people are using /24s as their service blocks for Anycast. So if you have one DNS server and you're going to Anycast it, you have to use a whole /24, one /32 out of that block, and to spread that out, and that seems pretty wasteful. However, when you're doing things like DALNet, which has 30 sites, or I don't know exactly how many, but they have a lot of sites, and they're using one block for all those sites rather than 30 separate blocks. So for them to maintain routing on their own, it would be much more expensive on the allocation side if they weren't using Anycast. And if you're efficient and you really have a need for a lot of IP spaces in that, or IPs in that block for web serving or what have you, it's not a waste. It's actually quite efficient. So carriers and peering. For content players, having your peering even is pretty important. So if you have, for instance, peered with a European network in, say, we'll just say California, you're also processing bits in Europe, chances are you may have just caused your European traffic for that particular network, those eyeballs, to go to California. So you have to really pay attention and think about who you're peering with, why, and where. It changes it adds an extra dynamic to that. So having like a European transit provider in the U.S. also can cause problems like that. So if you're buying transit from somebody that's predominantly eyeball heavy in Germany, and you're buying it in the wrong place, it could really throw off a network.
And to be clear, that also means, say you peer with European carrier X in London. You are better off not peering with them anywhere else. You do not want to peer with them in Ashburn. You do not want to peer with them in Chicago. If you drop that session, you want them to find an alternate path domestically. So you want it to fail over to your local transit or something else. You don't want them to go, oh, I peer with you in San Jose. That's clearly the next best spot now that London's gone.
Yeah. So when you're peering, you should really keep in mind that a peer might isolate, your traffic to specific nodes or specific POPs, or you may have other needs to peer with them in other places. You just got to select what if your Anycast is going to go over that peer or not. And when you're peering, do it where it makes sense. Think about it. Where are the eyeballs at? Who are the people you're trying to get your content to, and how do you want to engineer that? And it's really important to make sure that your peers and your transit providers know what you're doing and have a proper community set. So if something does go goofy, you can massage it and make sure that things smooth out. So benefits. Do you want to talk to benefits?
All right. So as a content player, what can Anycast help with? First and foremost, BGP converges really slowly, but not nearly as slowly as DNS. So it allows you to shift traffic either intentionally or unintentionally a lot faster than any sort of DNS-based wide area load balancing. Obviously, it provides you buffers for major failures due to that convergence time. So stuff might break, but that's okay. Your traffic is going to go somewhere else. It is a relatively simple way to manage your inbound traffic. It is BGP. And more importantly, it's BGP that you don't control. You're really putting the onus on the people that are delivering you the bits to make sure that their IGP costs are in line with what you expect for performance. And there's not much you can do about it if it's not. Now that said, when that occurs, there's obviously a huge performance upside to delivering packets at closer locations, either topologically or geographically, or in a perfect world both, which allows you to boost the performance of your application.
Also, with HTTP, there's a significant cost when using DNS to do geographical load balancing or whatever, finding the nearest site, that kind of stuff. And you end up, if you look at a lot of the sites out there, require 6 or even more DNS lookups to acquire the content. So when you're using Anycast, it trims that down quite significantly. And the other neat thing about it is it gives you a simple ability to write tools around it. So you could write interesting Perl scripts or whatever it is that you like to interface with your router and make a web interface that a NOC technician can say, hey, I want to shift all of our web content during our maintenance window to this other POP while we're working on it. Click, click, done. Traffic shifts. And you don't have to worry about any DNS, so people crashing zones and weird TTL issues and people doing non-standard things with DNS.
So what we did is we collected a bunch of data from a few different sources for May 9th. So Renesys provided BGP data. And in our case, what we do is we track which POP somebody is going to. As in each POP, the load balancer or the BGP speaker puts their own IP as the atomic aggregator. So we can look at both AS path changes and actual POP changes. We use Keynote to actually monitor TCP availability as short-lived sessions and compare that to the Keynote Business 40, for better or for worse. And Revision 3 was nice enough, Jay Adelson's company, to let us share their data. So May 9th was a pretty popular day for them. They released a new video, which they do every week. But it worked out to, we measured over 7 terabytes of transfer. So a fair chunk of data delivered over TCP Anycast for the day. So Renesys. For the day, they saw 130 BGP updates. That is considered for them a pretty low volume of updates given the number of BGP feeds they have. We did see 34 POP changes, which for us is a pretty big number for a given day. And we'll get to that in a second. We can attribute them mostly to one event. Like I said, 130 updates, pretty stable prefix as far as Renesys is concerned. So we had an event in San Jose that was an upstream event that generated 98 updates out of 130 for the day, but in this about 40-minute period. And that was 20 actual POP changes during that 35-minute window. That is single changes, so that's went from San Jose to Chicago, then back to San Jose. We said one change, so it's actually a failover and failback. Unfortunately, we actually couldn't match that up to any of the traffic changes that happened. I think there's a couple of reasons for that. First, most of the BGP speakers that we did see seem to be European and Asian carriers reporting their domestic paths to Renesys. Thankfully, most of those actual eyeball bits come in Tokyo and Amsterdam, respectively. So one possibility, and it is a big question mark in my mind, but one possibility is that there just weren't a lot of people using those routes. And number two is we don't have a big enough sample size. We don't really care as a company if our prefix is reachable to the internet at all times. We care that it's reachable to the people who are requesting our content at all times. And oftentimes those numbers differ by quite a bit as far as what prefixes are generating requests versus where we are unreachable when these things happen. The other interesting thing during these events, the average time between San Jose to Chicago back to San Jose was about 20 seconds, which also seemed very high to me. So whatever event happened was very, very quick on the trigger to go back to San Jose. But that's still enough if you're not sharing state to break all of your TCP sessions that were going on at that time. But for the most part, BGP seems stable. So then we said, okay, Keynote, tell us, is TCP actually stable? And evidently it's not.
Yeah, so just kidding.
So what we did with Keynote, they did 31 locations. Each location polled once every 5 minutes, so about one poll every 10 seconds. And compared that against the Keynote Business 40, which is just their index of business-like pages, I guess. And the same sample period that we used for the TCP data and for the BGP data. I don't know if this is going to show up. The green line is the Anycast measurement, and the orange line is the Keynote Business 40.
So if you look at stability, we pegged 100% stability.
This is the bottom graph.
On the bottom graph, so it's really hard to see the line. And on the top graph, our latency and time to load the data was lower than the average Business 40.
And it was a 30 kilobyte file that each one requested. So I think the average latency for the day to do the request was like 1.5 or 0.15 seconds or 150 milliseconds. So you can do the math on what Keynote perceived the actual download performance to be during the period. And finally, we have the Revision 3 data. So we looked at all the downloads for the day. It was isolated to a specific VIP. And what we did is we had a span port basically looking at TCP sessions that started at a POP that did not begin with SYN. which is very indicative of a session that was started somewhere else to that destination IP and all of a sudden switched over. And what we have a global state table. So we actually, all the load balancers talk to all the other load balancers every 5 or 10 seconds or so, and they know what source and destination port are destined to what pop. And they actually, in the event that we do failover, they actually do some magical things and get it back to the right web server. So we compared sessions that appeared out of nowhere to the intelligence we had about where the sessions were to begin with. And we wanted to measure long-lived data. So for the day, they had approximately 685,000 TCP sessions for the day. We threw out anything less than 10 minutes. So all TCP sessions that lasted less than 10 minutes, that data went away, leaving us with about 25,000 TCP sessions, which lasted longer than 10 minutes. You can kind of see the distribution on the graph of the number of sessions is the y-axis, and the minutes, the length of the TCP session is the x. And you can kind of see it's kind of the distribution I would have expected. We're talking, I think the average file size today was about 300 megabytes. And we observed a total of 4 TCP sessions move between POPs, which works out a failure rate, including the first 685,000 number, to 0.0006%, and for the long sessions, 0.017%. I would say, in my experience, it's tough to say that's any different than what we would have seen delivering a unicast service. And moreover, it doesn't deal with total failure rates. There are all kinds of other ways things could have failed that would be very similar to unicast. We were only looking at things where session started in site A, magically appeared in site B.
And keep in mind, if you keep state, that percentage is actually 0.
Yeah, in our case, we dropped 0 of those. But if you had something that knew nothing about Anycast, you're just deploying random TCP service that's got long-lived sessions, you would have dropped 4 out of 24,000 if you had the same source prefixes sending you the traffic and the same carriers that this particular customer had. Some networks are more stable, some networks are less stable.
So there's a number of gotchas when it comes to deploying an Anycast setup. So large-scale changes on the provider level really can impact your traffic. So you do have to pay attention to that and figure out, okay, what did somebody change? Is there a community that's no longer available that was? Am I leaking to something that I shouldn't be? And then things that are pretty bad get much worse. So you could probably talk to that.
There was a insurance company based out of Phoenix that was having some definite issues reaching our content. And through the course of talking to the right people, I finally got to the guy in charge of the network. And they had very strict requirements. They needed 2 T1s from their carrier, and each one needed to go to a different POP. The carrier in question was Sprint, and one POP was Anaheim, and one POP was Dallas. And they thought per packet load balancing would be a very good idea to get the best performance out of their 2 T1 links. That doesn't work with Anycast. What happens is, say first packet goes out east, second packet goes out west. Eventually one side gets really fed up and sends a reset. Because you're sending packets there that it has no idea what it's talking about. And in our case, it's before our global state change stable converges. Because it's during the initial setup where we're seeing these packets occur in POP A and POP B. It's not 20 minutes later into it. It's sin, ac, does not work. Nor would I expect they saw very good performance in general to any unicast prefix using this methodology, just because TCP would not have been very happy with the jumps with the round trip time.
So here's our conclusion. In our experience utilizing Anycast, it's not any less unstable than it's actually very good. It's a wonderful way to manage your traffic, and if you're able to dedicate the right resource to it and the right management to it, it'll make deploying HTTP and other TCP apps much more robust. And there's
we've all looked at, there's a reason that people always say TCP Anycast doesn't work. And the answer is that people publish data that supports that theory. And we're not really sure what the differences that make it not necessarily seem as stable in a typically measured environment. it'd be interesting to see. I know there's other companies here who don't necessarily talk about it that do TCP Anycast. I can count on 2 fingers the companies that I share my data with. But it would be interesting to see people who, VeriSign has done presentations in the past saying, don't run TCP Anycast. It would have been interesting if they could have published the failure rate for people that queried the GTLD servers with TCP, how often their actual traffic failed. Because, from our perspective, we're looking at our actual traffic, what happens on a daily basis. And VeriSign said, well, we saw traffic changing, so you shouldn't use TCP. But I would have liked to see, and I'd like to see other people share more data where they say, here's where our TCP breaks, because we do have it deployed, and this is what we've had to do to go around it.
And yeah, just trust us, it works. And widespread failures are going to cause some problems for you. But as long as the internet stays fairly stable, and it does, that doesn't happen too often.
Yeah, so IPv6. At CacheFly, we do have a plan.
The remote works.
And the plan, we just hope we're dead. Thanks. So what can you do? First, if you don't know that it doesn't work and you haven't tried it yourself, don't tell other people you know that it doesn't work. Because it's really frustrating when people say, oh, I heard from some guy who read some report that some guy published based on some guy's data that it's not going to work, so don't even think about running it. Moreover, if your application doesn't handle TCP failures well, I would not recommend deploying it on the internet. Because you can expect that your packets will get dropped somewhere at some time. And if your application doesn't support that, you're going to have problems regardless of how you deploy it.
So SMTP works well because it has some internal recovery mechanisms. HTTP works fine if you break an image. People are used to that. And people also, a lot of browsers support resets. So if a reset hits the browser, it'll retry. So in a lot of cases, it won't even impact the browser. And we suggest that you experiment with it and then collaborate and share your experiences. Any questions? Start over there.
So, Mark Hoster's VeriSign. I'm actually one of those guys who did one of those presentations. I think it's, there's 2 comments. One is, I think it's dependent on the client base that you're dealing with. And our client base was very far flung, looking at JRoot. And a lot of the ones that we saw were from far reaches of the internet. And there was definitely per packet load balancing sort of issues going on there. So that caused a lot of state changes between the 2. And so I think it's a question of how big of your clientele do you want to reach at all times? And do you just want to worry about well-connected spots or places that aren't as well-connected that may have some sort of brain damage sort of connectivity going on between?
Yeah, in our case, we want to reach places where our customers pay us money to deliver things to.
So, and it sounds like you've carefully engineered your network to do the right thing.
Yeah, for our business case, it wasn't a question of, hey, let's deploy it, and if stuff drops, we'll deal with it. We actually had to take the time to, to meet the SLAs that we provide our customers.
Okay, so in that sense, it makes sense. But there's cases if you just put these sites out willy-nilly, and you're trying to have global 100% connectivity where it works in the unicast environment. And it doesn't work all the time in an Anycast environment. And that was the point I was trying to make.
Is that Randy?
Randy Bush, IIJ. It's good to hear this talk on about the 10th anniversary of many of us deploying this stuff. And I think Mark's point is, and your response is, it's probably good if you engineer it. I think that applies to more than this. But there's one point that I have a problem with, which was that you wanted to narrow peering and narrowing your topology. And I'd reflect back on the engineering part. There are circumstances where that is exactly not true. And for instance, the deployment we did back in '96, the purpose was to shed traffic off our backbone. We didn't have, we had to support a very high traffic streaming program. I don't remember what popular TV thingy they were streaming. And so what we did is we TCP Anycasted it from all our edges to our peers. And that's the exact opposite. Okay, so I think the point here, both to Mark and to other people thinking of deploying, is you might engineer it.
Yeah, to speak to that, the talk we're giving is specifically content that we were dealing with directly, and we were engineering the network to deal with our particular content and our clients' needs. But in that case, that would be a different engineering requirement.
And it's not to say that definitely to make it work requires a lot of time, a lot of engineering. I think the point was more that if you don't, it's really not as bad as you might think it is. And there's possibilities, depending on what you're doing, where the potential benefits of doing it and the simplicity involved might outweigh, like I say, if you're dealing with an application that can tolerate unreachability and deals with the fact that from time to time IP addresses can't be reached, if that's the application you're deploying, Anycast is a really easy way to start getting your feet wet, as it were, in distributing your services to more than one data center. Woody?
So over the past 10 or 12 years, a bunch of us have all seen the same result, looking at long-lived TCP connections for content distribution. That is, we've seen over and over this number of about 1/100%, right? And Mark's numbers with the with which route? J route, were really surprisingly different from that at the time that he released that. And so, I don't know, I mean, the methodology was sound, it was just a different result. And so it seems like maybe that might bear some looking into at some point, is why it is that we're seeing this sort of bimodal result, rather than just
I think to
hammering on the
Randy's
two
point, it
modes.
also might have to do with purpose. I mean, I
Yeah.
think my stated
Right.
goal is a lot different than K-Root's stated goal.
Exactly. So I think that one mode of result has been very much this sort of large file transfer, right, or streaming audio or whatever, right, which is effectively the same thing. And the other has been a fairly different kind of network that normally carries fairly different kind of traffic. So we might kind of take another look at that at some point if it seems to hold up.
And
Yeah.
another interesting point would be that DALNet kind of runs very long-lived TCP sessions. I mean, some people go for months. So it seems to work for them. It'd be an interesting thing to study how that works. And I don't think they're terribly picky about who they get transit from. So it'd be, it's functioning for them and they're succeeding with it. So that would be another good study to make.
Yeah, Danny McPherson again. I just wanted to echo what I was standing here first. I just wanted to echo what Randy said, actually, and many others like Hank and others I talked to. Is 10 years ago people were using this to game Keynote for the same reasons, and for TCP-based transactions for a 10K file on a web server, lots of ingress points in your network, and there were significant improvements in response times because it's all propagation delay or round trip time related, or however you want to look at it. But so that was the one thing I know, so I don't think anybody can test that other than maybe one published thing. But and then the other part is I think that there are a lot of implications on things like origin AS or announcing a prefix from multiple places, and even folds into some of the security aspects and prefix hijacking, and some of those other things that this helps complicate. And so those need to be considered, as well as the state between different servers. That's what I suspected some of this might include, is how you synchronize some of the state between servers or content, and how you deal with the failovers if a process dies inside of that, just as with DNS or something like that. So that's all I wanted to say. So.
Yes, certainly this presentation could last a lot longer and covered a lot more detail. This was more just an introduction of, hey, it's really not as scary as everybody thinks. If everybody started playing with it, perhaps we'd have more data points that we can use to learn more about why things behave the way they do.
And some innovation can happen out of that. Some open source state synchronization tools, things like that would be pretty fantastic.
Michael Sinatra, UC Berkeley. I agree that it's nice to see more empirical studies like this, so thanks for doing that. I wanted to say a little bit about, at the very end of the presentation, you did say that not all protocols, not all applications can handle this. And I would be careful about saying, then generalizing, because your presentation does say TCP, and I'd be careful about generalizing that to all of TCP. So you may want to be a little more careful about how you present it right off the bat instead of throwing that in at the end.
When we were saying protocol, we meant, 4 through 7 kind of protocol.
Yeah.
As a transport, we think TCP works great. The question is, what does your application do when the transport goes away?
One other thing I want to say is, part of the reason I think people object to this is that the TCP protocol does provide ways of dealing with out-of-order packets, the idea being that packets may not always take the same path. Because the protocol allows for that, it allows people to do that in their routing. And we don't know when or where that will happen. If not many people today are doing per-packet load balancing or traffic sharing on their links, maybe they will start. Maybe a new implementation will come out or a new router vendor will start making that their default. You just don't know what's going to happen. So you do have to be very careful with this sort of thing and watch out for that.
Yeah, Matt Peterson. 2 quick questions here. The first is you mentioned this, I think the first slide was high definition adult content. Can you kind of give a description of the size of the files? Because your comparison data was, I assume, a highly compressed podcast or video, and that's quite a bit different than something like HDTV quality video files. And the second question is the state mechanisms. You mentioned open source. Are you currently using a commercial product, or do you hack something together open source and you're looking to extend that?
Sure. As far as the content itself that we measured, it was actually a mix of a bunch of different compression algorithms. I forget what they publish in, to be perfectly honest. You can go to revision3.com and look at any of their shows. You can see what they use. But average file size, like I say, was about 350. They have some that are about 200, the small format stuff. And they do have files that go all the way up to about 650, 700 megabytes. So it was kind of in the range of there. As far as what we do for state, we kind of hacked it together ourselves. It's probably something that's we wouldn't necessarily go out of our way to publish. We'd probably be more interested in supporting some sort of more open source, something that was more community or grassroots based, and go ahead and put some money behind that than necessarily release our code. But it's definitely something we want to support so that more and more people can kind of play in the arena, as it were.
Hi, Nathan Patrick from Sonic. I'm sorry, we're running late, so I'll need to cut this off. I had tried to close the lines at least. If you have more questions, please talk to them offline. I'm sure they'll be around.